Okay, this is video number 3 in Module 1. Once again, going with the material in the textbook by Webster. We've talked about ways that biomedical signals can be classified. There's also for biomedical signals, in addition to thinking about the statistical properties as well as some of the sensitivity of instruments, etc., there are time and frequency characteristics associated with biomedical measurements. So instruments are also classified or described by the temporal and frequency responses to inputs. Most instruments or physical processes can be modeled by some kind of differential equation, shown here, equation 1-14. Now, this is an nth order differential equation in y, and as a general rule, we assume that n is a higher order than m, which is the highest order derivative of x. That's not always the case, but often it is the case. So here is an example of a differential equation. This models some physical process, and it has coefficients associated with the y variable as well as the x variable. We generally assume that we can model these systems as linear differential equations. This is an example of a linear differential equation because it does not contain anything squared or any sinusoidal terms. It only contains x and y and their derivatives. So the easiest way to solve a differential equation is to use the Laplace transform technique, which is actually not covered in your textbook. But as a general rule, most people who have been through an undergraduate science or engineering degree are familiar with the Laplace transform technique. Basically, a differential equation is transformed into the Laplace domain. It is solved in the Laplace domain, which is an algebraic solution, and then the inverse transform is taken. If we're interested only in the frequency response and we're not interested in the temporal response, we can take the Laplace variable s and we can let it be j omega, in which case that differential equation transforms to something that looks like this form here, where we have powers of j omega, meaning that if we have a sinusoidal input of a specific frequency, so if omega is known, we're basically going to have an output that has both a magnitude and a phase in general. So first of all, if we look just at a zero order system, what would that look like? That would just have a constant times our function y of t is equal to a different constant times our function x of t. And in your textbook, he does not use the Laplace variable s. He uses the differential variable capital D. So basically, if you're from an electrical or mechanical engineering background, you can just substitute s for D for everything he has in his book, and generally that will be a perfectly valid thing to do. So if you take and look at a transfer function, which is defined as output over input in the S or D domain, y over x is y of j omega over x of j omega, which is just simply b naught over a naught, or k, a constant. And what we really have there is the static sensitivity. And notice that we don't have anything associated with a y offset here, because basically when you're looking at the temporal characteristics, as a general rule, that would make the differential equation inhomogeneous, which is fine, but it's usually just corrected with a constant. So since we're solving for constants anyway, if we have initial conditions in our system and we're concerned with transient effects, then that can be figured in. So for the zero order system, we just have static sensitivity, and that really is our only variable that characterizes the system, and the output over input is not a function of the frequency of operation. Now, if we look at a first order system, that would be a differential equation represented here, where we have a first derivative of y, and then y shows up, and then we have some function x of t, or we have the variable x of t. If we now take the transformation of this differential equation and convert that to the frequency domain, we find that our output over input looks like the following. It's going to be a constant k, which is going to be some combination of a1, a0, and b0, divided by another set of constants and variables, 1 plus j omega tau, where tau is a constant and omega is our variable. So if we put that into phase and magnitude form, it looks like this. So our variable here is omega. Tau is a constant and k is a constant, depending on A1, A0, and B0. And so we find that our output over input in the frequency domain is going to be, our magnitude is going to be inversely proportional to frequency approximately. So as frequency gets very large, this magnitude number will get very small. As frequency gets very small, this magnitude number will get very large. And so we find that for this differential equation, that's the case here. So it's acting like a low pass filter because as omega gets larger and frequency gets higher, the output gets smaller. Now that's just for this particular differential equation. There are other types of first order differential equations, other arrangements and other sets of constants, and so those would be, give you a different result. Anyway, when you transform that back to the time domain, it's going to look like some constant k times 1 minus e to the minus t over tau. And notice this is basically a transient effect that is dependent on tau, which is a function, once again, of our constants. So let's look at an example of a zero order system. We discussed earlier the linear potentiometer. It's written about extensively in the textbook in chapter 2. So we'll actually describe a little bit about the linear potentiometer in the next chapter. But it's an example of a zero order system because basically you're looking at an output voltage as a function of input voltage. And so the linear potentiometer is just nothing more than a voltage divider. And the voltage divider and the voltage output is dependent on the position of the sliding contact. So because of that, it's a straight voltage divider, and as a function of x, then you just get a nice linear output. So that's not frequency dependent because the resistive element gives you a direct relationship between position and voltage. So this is what a single order system or zero order system would look like. If we put a step input in other words, if we do an instantaneous change of position from 0 to x1, then we don't have any time delay characteristics in our output. We just get an instantaneous change in the output. For most resistive elements, this is the case because any inherent stray capacitance or inductance in the system would be so negligible to the time scales that we're actually making a measurement that it would look exactly like what you see here, and there would not be a frequency response. The phase shift is 0 because there's no imaginary component in the output, and the magnitude is going to be constant in time and also constant in frequency. This is an example of a first order system, the first order system that we had the equations for. This is a low pass RC filter where we're inputting a voltage across this terminal pair, and our output is the voltage across the capacitor. And so if we just look at the static characteristic of output to input, we have a slope that's k. So if we have a constant input that doesn't have variation with frequency, the output is proportional to the input. So for DC, basically this looks a lot like our previous example where the output is equal to the input instead of being scaled. So if we now have a step input, what we find is that the output will change in time, and it also changes in frequency. So if we look at sort of a frequency input, we find that for frequencies that are sort of below the cutoff, which is defined by the values of R and C, we have a fairly flat response. And then as frequencies get high, that output of the magnitude starts to decay. So we will not have a constant output across frequency like we did in the previous example. The outputs actually decays as frequency increases. So for very high frequencies, we're approaching a zero output. And notice that our scale here is a log scale. Now, if we look at the response to a step input, so the step input just goes from 0 to 1 instantaneously. What we find with this kind of a system is that we have a delay. From an electrical engineering and mathematics point of view, the step function contains, because this is an instantaneous change, if we were to do a Fourier analysis of this input function, we would find that it contains a significant number of very high frequency components. Because those components are filtered out to a great extent, what that means is you're not going to reproduce this sharp edge of the step if you're putting it into this filter. So you're going to have a function that smoothly approaches 1 with some time constant. So this is an example of when the time constant is small, you're going to approach 1 relatively quickly. When the time constant is larger, you will approach relatively slowly. The phase is going to transition based around this cutoff frequency associated with the filter. And so you find that you start with 0 phase at DC, and then as you go to very high frequencies, you have a negative 90-degree phase shift. So that's an example of a first order system. And so not only do you have your static sensitivity for when you have DC inputs, when you have temporal inputs, you have this combination of frequency response, which is a steady state thing, as well as temporal response, which means that you're limited in how quickly the instrument can respond by the time constant. A second order system is similar. It would have a second order differential equation in Y. The author has an error here. This should be an equal sign, not a minus sign. So you've got your Y equation, second order, equal to your B naught x of t. If you take the differential variable transform there, and what's been done from the first line to the second line is basically you substitute for the derivatives with the differential operator, and then you divide through by the constant a naught, and then the constants are rewritten as omega n squared and 2 zeta over omega n. And the reason for this is these correspond to some physical parameters associated with a natural frequency oscillation and a damping rate. So we'll show a picture of that on the next page. So the other error that your textbook author has is that once you substitute the differential operator, you don't mix d and t, so really this should be y of d and x of d. The equations that are provided by the textbook are provided as figures, so I can't go in and change them, but you just need to be aware that that is a textbook error as you're reading through your book. So once again, this one is correct. So here we have y of d over x of d, and so we're solving for output over input. And so you can see that output over input is a rather complicated function where k is a constant. D is our differential operator, or analogous to S if you're in the Laplace domain. Omega n is another constant, and zeta is another constant. And those constants would all be dependent on A2, A1, A naught, and B naught. If we now substitute j omega for d, so what you do when you make the substitution of j omega for d is you're actually looking for the steady state response about omega. So we're looking at a steady state response for a given omega. We find that it looks like it's of the following form, where we have a magnitude term and a phase term once we convert from a rectangular to a polar form of those variables. Here is an example with some specific constants. This is a spring mass, a damp spring mass problem. And so if we have these constants, then it turns out our k is going to be 1 over k sub s. Our omega n will be k sub s over m. and our zeta will be b over 2 times the square root of k sub m. This is referred to as the damping factor, and it can be greater than, equal to, or less than 1. And this is the natural frequency. So if this were a spring on a mass problem, B would be a frictional constant, K would be a spring constant, and M would be the mass. So we get these damped oscillations. Now, a lot of this depends on the relative values. When you solve for this, it depends on the relative values of omega n, zeta, and so on. And so your output can be in the frequency domain. Your output can be real, imaginary, or complex, and based on sort of the relative values of A1, A2, B0, A0. And so that can yield 3 different possible solutions to that differential equation. So as you might remember from differential equations, all second order differential equations that are linear fall into this category where you have a second order algebraic equation if you do a Laplace transform, and then when you solve that quadratic, you can have a real, an imaginary, or a complex solution. Or you can have a double root. Now, we're not considering the imaginary solution because that would be a case where you had no friction, which doesn't really happen in the real world in a mass spring problem. So we would consider only the complex and the real root. So you can have 2 different real roots, in which case you have what is known as an underdamped problem, or you can have a double root, which is known as a critically damped system, or I'm sorry, the 2 real roots is known as an overdamped problem. So you basically, in that case, you would get the following kind of solution where you have 2 different time constants. So if you look here, this is the damping factor, and the entire thing of this times omega n is 1 over a time constant because this is of the form t over tau. So when you have this, when you have 2 different time constants, you basically have 2 different exponential decay rate functions. So usually one is negative and one is positive, so you'll have kind of a dominating rise time and then a dominating decay time. So this is the overdamped solution, which would mean you had 2 real roots. The critically damped solution would mean you have a double root, and then the underdamped solution would mean that you have a complex root. In the case of the complex root, you find that you just get 1 time constant, but then you get a sinusoidal function. So the underdamped case is decayed sinusoidal oscillation. The overdamped case is sometimes a complex rise time, and the critically damped case is the same. So I've got some pictures of these. Here is that response time as a function of time. So you see that in the case of the underdamped, here's your step input, and your output's gonna be 1 over k sub s, where 1 over k sub s is your slope. So if your input is 1, your output's 1 over k sub s. What happens in that overdamped or that underdamped case is you overshoot and then you oscillate around your final value until you slowly reach it. In the critically damped case, you basically have kind of an optimized trade-off where the rise time is as fast as it will be here without oscillation. So if it's critical that you not overshoot your final value and you have no oscillation, but yet you want as quick a response time as possible, the critically damped system will give you that. And then finally, the overdamped system has a slower rise time and a smoother function and also no overshoot there. These can be defined based on this parameter zeta. So if zeta is less than 1, the system is underdamped and it's going to oscillate. If it's equal to 1, it's critically damped, and if it's greater than 1, it's overdamped, which is going to slow this rise time. These curves on the right show your frequency response. This is the magnitude response. For that underdamped system, you get a little resonance peak here. For the critically damped and overdamped, you basically just get a decay at the cutoff. For the overdamped, you actually would have two um, separate points where you get a change in slope. Um, and so it's kind of, but because they're so close together, it looks like a continuous curve. And then here's the phase, and you can see that the phase transition, the total phase transition is the same. It's just going to occur more rapidly or more slowly, depending on whether you're overdamped, critically damped, or underdamped. So the last topic in this chapter is just the design process for medical instruments. Um, there are some flow charts that are given in your textbook that you can look at and see just sort of what your thought is, what the thought process is. So you have a measure-in, which is what you want to measure. And then here are some of the things that you would consider. You would consider what are some of the factors of the signal. What is the sensitivity? What's the range? What's the input impedance? What's the frequency response like? How accurate is it? How linear is it? How reliable is it? These are some of the things that we have discussed in this chapter. You're also interested in environmental factors. So are you going to have a noise problem? Is there going to be movement? Do you need a lot of power? Does it need to be small? Are there going to be vibrations? Is there going to be ambient changes in temperature and pressure? And then medical factors. Is it going to be invasive or non-invasive? Are there toxic materials or radiation involved? Will it be uncomfortable or painful? And then finally, economic factors. What's it going to cost? Is it easy to make it widely available? Will it be easy to warranty it? Will you have consumables? And is it compatible with existing equipment? So taking all these factors into consideration, typically you'll come up with some kind of initial instrument design. Then from there, you'll do some testing with a prototype, then some final design, an approval from the FDA, and then production. Now, what's missing here in this series of steps that is becoming more and more prevalent is a simulation. So many times before the instrument is prototyped and after it's designed, there will be extensive simulation done using some kind of simulator package. And so that's kind of missing from this book, which is slightly older. So what does the FDA do? There are basically things are divided by date. And that was May 28th, 1976. So if you've got pre-amendment devices, then all of these, most of those are analog, and they're used for all different kinds of things. And back then, things were divided into one of three classes, and it depends on safety and effectiveness. After 1976, unless they are substantially equivalent to a previous device, they're all placed in class 3, which is the more stringent category and greater regulation. And so there are a number of things that examples that are given here. Now, if you have a substantially equivalent device, then they're assigned to the same class. So this would be, for example, the old EKG machines were analog. If you now have a digital EKG, that now is a substantially equivalent device because all you really changed was the readout. Implanted devices are always assumed to be class 3, and this might be pacemakers, things like that. Custom devices would be orthotics, dentures. They're exempt from pre-market testing, but they are subject to general controls. Investigational devices are also exempt. Artificial heart, some of the things that are used in blood purification or oxygenation, some of those kinds of things are considered investigative devices. And then transitional devices, these were regulated as drugs before, and now they're defined as medical devices, and so that would be things like injectable silicone, intraocular lenses, surgical sutures, soft contact lenses, and the like. So those are a few of the sort of general categories that the regulatory environment considers. Um, and so that gives you, something to consider when you think about device design.